Yeah, hi, hello everybody. I hope that all of you are doing very well. So this is today's lab. I couldn't record the lab early. I just explained the experiment to you without starting the camera. So that's why I'm recording this session for you guys. So let's get started. And today we will talk about atomic spectroscopy. So what do we mean by atomic spectroscopy? So simply guys, if we have a discharging tube, like hydrogen discharging tube or maybe mercury discharging tube, and we apply high voltage across that tube, we will see that there is a light. What's the reason for this light? And it will give you here example. So here we have a hydrogen discharging tube, and the hydrogen discharging tube, guys, can be a very good example to explain what we have right here. So if we try to come to this simple diagram, so in this diagram I try to explain how the hydrogen atom is excited. So the hydrogen atom is simply proton and electron. So if we excite the atom, that means we excited the electron itself. Okay? So if we come here and look at to this electron. So maybe I need to get you closer. So I will try to do that, so you can see what I'm talking about. Yeah, so let's go closer, guys, right here. Perfect. So if we excite the electron, that means we provide the electron with energy. So what will happen if we provide the electron with energy? So the thing that can happen, guys, is that the electron that you can see right here will jump to higher energy. Jumping to higher energy doesn't mean that the electron has different position. No. Jumping to higher energy, that means the energy of the electron is changed. So the electron will stay at that level for some time, which is the lifetime, and then go back. And when the electron go back, you will see that there is light, photons will be emitted. So this is very nice. And this is the mechanism, guys. So energy absorption from the electric discharge, and then energy released as photons. So this is what will happen, guys. Okay, so this is the high energy state of the electron in the atom, and this is the low energy state of the electron in the atom. So that's very nice. And if we go down, you can see here down, you can see that we have the hydrogen as a hydrogen molecule. When we apply the high voltage, so what will happen? The high voltage will dissociate the hydrogen molecule. So what will happen here? We will have two hydrogen atoms. And then that discharging voltage will provide the electron with some energy. So that will help the electron to jump from lower energy to higher energy. Now if we come to the other side, right here, and it will go back a little bit, guys, so you can see all of that. Okay, maybe I need to move this a little bit up. So let's do that. Like this. So just move it a little bit up. Yes. So if we come here, guys, you can see that we have the visible light. The visible light simply can be presented as a spectrum. So we have red, orange, yellow, green, and violet. And you can see if we go from the red to violet, so we will have shorter wavelength, higher frequency, higher energy. If we try to figure out the equation that can describe the relation between frequency and wavelength, so that equation is frequency times wavelength gives me c, which is the speed of light. To find the energy from frequency, you need to multiply frequency by Planck's constant. So that will give you the energy. Perfect. All of these are simple explanations, simple ideas that can help you to understand this topic. So now I will go, or this experiment, I will go a little bit closer, like this, and now try to explain what will happen if we have a spectrometer. So here, guys, we have the spectrometer. I will show you the spectrometer. Here we have the diffraction grating, spectrometer, and we have a light source, which is the hydrogen light source that I showed you guys. So to show you the spectrometer, so this is the spectrometer, I will show you that. So this is the spectrometer, as you can see right here. You can see the diffraction grating, which is what you can see right now, this white square that has a window in the middle. Okay, and this is the spectrometer that we are using. Perfect, very nice. So now, let's try to explain what will happen. So I have the spectrometer here. I have the front tube from the spectrometer go to the light source. The other one, which is the microscope, goes to my eye. So if I move this microscope to the right or to the left, so what will happen? You will notice that there are some colored lines or spectrum. So for hydrogen, for example, so you can see the violet, maybe you can see the blue. So you can move the microscope maybe to the right or to the left. So you will have the same spectrum to the right or to the left. So this kind of spectrum is symmetric. So what you will have in the left, on the right, will be on the left. Okay. So this is what we are using. So now, using the spectrometer, you can observe the spectrum through the diffraction grating. Now let's come to the experiment and what you need to do here. I will go again a little bit up, like this, a little bit up, so that's very good. And now, try to explain part A and part B and part C. So in part A, from this experiment, guys, you need to create standard equation. And you did very nice work today. I helped you a little bit, but you did very nice work, guys, to figure out this standard equation. So what you need to do, guys, when you move the spectrometer, the microscope and the spectrometer to the right or to the left, for example, you need to measure that angle. So the spectrometer has a micrometer that can help you to measure the angle when you rotate the microscope to the right or rotate the microscope to the left. Measuring that angle and then figuring out the position of the line. So if we come here, if you know the angle theta that we have right here, you can use that angle theta to figure out the distance. For example, for the midline. So you can use that to figure out the distance for the red line, for example. Do that for Mercury, and the Mercury would be our standard. So do that for Mercury. You need to measure the angle theta for each one of the spectrum lines. So each line spectra will give you position. And you will try to measure the angle first for this line spectra, and then calculate the position for the line spectra using this equation. So x is equal to d tan theta. Okay? So the distance d here represents the distance from the light source to the diffraction grid. Okay? So we know d, we can measure d, it's not hard. Now guys, when you plot wavelength, you might ask me, how can you find the wavelength? You can find the wavelength, guys, for Mercury from the worksheet. So the worksheet can provide you with the brightest line spectra in Mercury spectrum. So you can use those wavelengths, compare them with what you have from the Mercury discharging tube, and then have set of data, position, angle, wavelength, use the angle to calculate the position of the line spectra, and then plot wavelength along y-axis with respect to position along x-axis, and that should give you straight line, as you can see right here. Fit that with equation, so that will give you this equation that you can see right here. And this is called the standard equation that can be used to figure out any wavelength for any source of light. For example, if I'm using, for example, hydrogen discharging tube or sodium discharging tube, as we have in this experiment, so it will be easy for you to calculate the wavelength for the line spectra that you have from those light sources. Perfect. And then, if we go a little bit down and just mention to part B and part C. So, in part B and part C, you are going to use spectrum from hydrogen atom, and in part B, you are going to use spectrum from sodium atom. Again, guys, just to remind you, to prepare your report, please go through the guidelines that I give you in the syllabus, how to prepare your report. Go through the worksheet, and the worksheet will tell you what do you need to do. So for this experiment, you just need to figure out the wavelength for hydrogen spectrum and wavelengths from the sodium spectrum. So, and you need to use the standard equation that we have from Mercury discharging tube to figure out those two wavelengths. Again, guys, in future topics we will use part C. So we will use this data, which is the spectrum from the hydrogen atom. So we'll use this data in future topics. So this is a very nice experiment. This experiment can teach you, can help you to learn how can you have fingerprint for each atom in this wallet, just using simple idea, which is the spectroscopy, atomic spectroscopy. And I will show you that here in this, so maybe I need to move a little bit right here so you can see that clearly here. Okay, so you can see here, for example, you can see spectrum from lithium, spectrum from potassium, spectrum from sodium. This is spectrum from sodium that we did today, spectrum from hydrogen that we did today, the spectrum from mercury, which is what we did today, and we use that as standard. So this spectra can be considered as a fingerprint. So each one of these atoms has its own atomic spectroscopy. So thank you so much, and again I would like to thank you. You did very nice work. You worked together, you collaborate together, and this is very nice. I'm happy. I feel that you have this lab as a challenge, and you were eager to know how to figure out the standard equation from the mercury discharging tube. Okay? So thank you so much, guys, and see you next session. Thank you.